So you may have heard the terms RGB, HSV, or CMYK. These are names of different color spaces, and what color spaces are, they're different methods by which we store images on computers. So you may be familiar now with RGB, which is how we store colors in various intensities of red, green, and blue. But there's also HSV, which is hue, saturation, and value, or intensity. And then there's CMYK, which is actually commonly used in printers or inkjet printers, K being black, by the way. So let's talk a bit about the RGB color space. Oh wait, is it the BGR color space? That can be a bit confusing because while OpenCV uses RGB as its default color space setting, the actual order in the array is BGR of the colors. Now there's a reason for that, and that reason has to do with how computers store memory. So as you can see here, even though we're storing it in BGR format, it actually is stored in RGB format. It's a little bit complex, and maybe you can dig into it on your own time doing some research. However, it's just a cool fact to know. And just heading back into RGB, which I may have already mentioned, it's an additive color model, which means that we mix different intensities of red, green, and blue to generate different colors. And it's quite useful. You can perhaps generate any color we can see with our eyes using this model. So let's take a look at another very important color space, which is the HSV color space. HSV stands for hue, saturation, value, / brightness, or intensity. Now this color space attempts to represent colors the way we perceive it, and it stores information in a cylindrical model which actually maps directly to RGB color points. Now in OpenCV, these are the ranges that the HSV scale goes up to. So the first value is from 0 to 179, second goes to 0 to 55, and value goes to 0 to 255. You may have remembered that in RGB they all go up to 255, sorry. So you may be wondering if HSV actually generates as much colors as RGB, and that's a good question, and the answer is in OpenCV no, because we're actually not getting all the colors mapped here, because how this represents colors is that you go a 360-degree circle around the cylinder, but in OpenCV we only go in 2 degree increments because it's divided by 2. So which means we don't have the same granularity in HSV as RGB. However, that's okay. We don't actually lose much in the real world of computer vision. This is more for high fidelity photography that it may matter more to them. Now HSV is actually very, very useful, and it comes in very useful in color filtering. If you want to learn more about HSV and HSL, which is another similar color space, you can look at these links here. They have some very useful information. Now color filtering is actually why HSV is so useful. This is actually a representation of a cylinder for OpenCV itself. So when you're actually filtering on color, we're actually filtering on the hue part of the HSV. So what I didn't mention before was that hue is essentially color. Saturation is vibrancy of the color. So as you can see in this cylinder here, everything kind of tends to go white at the center. So at low saturation, everything is white. And at high saturation, that's when you start getting rich colors here. And value as well is brightness. So as you can see, value here, at lower ends of the value, you get dark or black colors. And then going all the way up, you start getting bright colors. So this is how HSV represents colors, and it does it almost as good as RGB, even given this limited range here. So now back to color filtering. So while the hue goes from 0 to 180, you can see that into this circle here. If we would like to filter different ranges, this diagram gives us a lot of useful information to filter. So by setting the hue from 165 to 15, you can filter on red colors here, and then setting it at 45 to 75, you're getting the greens, and similarly for blue, 90 to 120, you can get the blues here. We're actually going to do some real color filtering in this course later on, but just remember this diagram which I created here is very, very useful for color filtering. So let's actually explore these color spaces using some code. So let's load an image here, and that image was actually the Louvre picture we loaded previously. So now let's look at the BGR or RGB values of that image. So by doing this indexing here on this image array, what we're actually doing is accessing the the 3 values that are stored in the first pixel location, which is 0, 0. So let's run that, and this is actually the values here. So we can see the blue, which is B here, corresponds to a value of 12, green 18, and red 31. So that's pretty cool. So we can actually play with this a little more. We can actually look at more pixels here. That one didn't change much, surprisingly. Let's look at this over here, and we get some new values. Remember, this image wasn't a highly variant image, like a very colorful image, so that's why you're probably seeing small changes if you're playing with your own values here. So now let's see what happens to these RGB values when we convert it into grayscale. So let's run the first line. As you remember previously, this converts an image to grayscale, BGR to gray, and let's print the shape that we get. So previously, actually we should print the shape for the last image file. So let's take a look at what this looks like. We see A30, 1245, and 3L. Wonder what we're going to get now. Just 2 dimensions. And as you may have remembered, I told you, when you store an image in grayscale, you're essentially converting it into a 2-dimensional array. So each pixel point now, and we can look at it by doing something similar here. Let's print this. You're actually going to get 1 value now, which is 22. So that's actually quite cool. And we can just get more points here. Similarly, this is actually the same thing. So now you've just seen the effect grayscaling has on images. So let's take a look at another useful color space. Well, actually HSV is extremely useful in terms of color filtering. So just have the ranges for you here as a reminder. Now, remember before previously, one of the arguments of the CVT color function was color underscore BGR to gray. Now we can see it's BGR to HSV. So we've created an HSV image here, and then we're firstly going to show this HSV image. Then separately we're going to show the HSV hue channel, saturation channel, and then value or intensity or brightness channel. Now we're doing this by indexing just that specific value in the array. So by putting the semicolon here, actually colon, sorry, this is saying we want all values of the first and second dimensions. So these are the widths, the heights and the widths, sorry. And then this is actually telling us we want the hue channel only here. And similarly, this is telling us we want the saturation channel, which is the second value of this index, and the third channel is a value channel. So let's run this code, and we can actually see the individual components coming out right here. Now this isn't terribly useful for anything other than just to visualize this as an exercise. So we can see the hue channel, and the hue channel is quite dark because it only goes from 0 to 180. And one thing you should note that's important here is that anytime you use the image show function, it's trying to show the image as a BGR or RGB image. So it doesn't actually display HSV images, because look what happens when we try to display an HSV converted image. Everything is totally messed up. I mean, the general image is here, but the colors are out of whack, and it's not terribly useful for anything, at least not to my knowledge. So we can look at the value channel, and this actually looks like a grayscale of the image, and in fact it actually is, because it's a brightness. And the saturation channel also looks a bit messed up, but it's good to visualize the HSV components separately so we have an idea of what we're looking at. So we actually can do that to the RGB channel too. So by using the OpenCV split function, it's a quicker way to do it, we can actually separate the components into BGR once an image is loaded as a RGB or BGR already. And then we're going to print the shape just so we can see what it looks like. And then we're actually going to show the individual components here. One thing to note is that because we're splitting the image here, it's going to show as a grayscale image in OpenCV because it's only going to have 1 dimension of color. Previously we had all 3, but now it's only going to take the red, green, and blue and show them as various grayscale images. However, if we use the merge function, we can actually combine all of them, and get back the original image. And what about if we wanted to actually add or amplify certain colors in an image? We can do that by adding plus 100 here. It adds 100 to every value in the blue matrix. If the value was close to 255, it's going to max out at 255. We can't go past that in OpenCV. So let's take a look at this code and see how it appears. So as we can see here, these are the individual image channels. So this is blue, move it away, green, not much to look at, and red, again, not much difference to look at. Now you should note, if I had an image that had separate green, blues, and reds significantly, that you would, separately, you would actually see a drastic difference. So now let's look at the merged image here. So we get back our original image by merging all three color spaces. Quite nice. Now, what about by adding the 100 to blue? Now, as you can see, the image has a very much a blue, well, actually almost a purplish tint to it. So this is actually how color filters and colors are created. You may have noticed movies like The Matrix sort of have a green and blue tinge at different scenes. That's sort of how that's done. But what if we wanted to see these green, red, and blues as actual colors as opposed to just grayscale images? We can use the same split function. However, let's create, using NumPy, let's create a matrix called zeros. And this may be confusing to NumPy newbies here. But what we're doing right now is that, so what exactly we're doing here is creating an array of zeros that are the same shape as the original image. So if you can see, if you run this line here, which is in the array, you get this 830 by 1245 dimensions. And everything using np.zeros, this makes everything, every element in this array zeros. So why that's useful for is that when we're actually using the zeros array here, this basically gives a layer of all zeros that fit in the same width by height dimensions as R, G, and B here. So let's run this code, and this is pretty cool. We can see that we have now individual components with the red, blue, and green tints that make up the image. So this is actually a pretty nice thing to see. So that's it for color spaces. Hope you enjoyed this section.